To understand true levitation, we first have to agree on what it actually is. We're looking for an object holding perfectly still in midair, relying on pure physics rather than camera tricks, magic, or science fiction. It's distinctly different from what astronauts experience in orbit. Floating inside the International Space Station is simply a state of continuous freefall in a microgravity environment. It also entirely rules out mechanical thrust. A helicopter holding its position in the sky relies on spinning murder blades physically pushing massive amounts of air downward. To achieve actual levitation right here on Earth, without moving parts, you have to directly overpower the invisible, constant force holding everything down: gravity. Think of the universe as a stretched piece of fabric. When a massive object like our sun sits on that fabric, it creates a deep curving dip in spacetime. And when a smaller planet like Earth sits inside that massive well, it rolls into the depression while simultaneously creating a smaller dent of its own. That localized downward pull is what keeps your feet planted firmly on the ground. You don't need to break the laws of physics to float. You simply need to harness opposing forces that are exponentially stronger than Earth's downward pull. One of the most surprising forces capable of pushing back against gravity is sound, specifically highly concentrated acoustic pressure. Sound is a physical vibration moving through a medium. If you turn the volume up high enough, those vibrations exert kinetic force on physical objects. You can see this clearly on a Chladni plate. If you vibrate a metal surface covered in sand using specific audio frequencies, the sand bounces wildly until it settles into perfectly calm geometric patterns. Looking at this diagram of intersecting sound waves, we can see exactly why the sand settles. Those calm pockets are called nodes. By aiming ultrasonic speakers directly at each other, scientists can stack these nodes into a three-dimensional matrix in midair. An object trapped inside one of these acoustic pockets is held perfectly in place by a physical bed of sound. The primary limiting factor here is simply scale. It requires deafening, jet engine levels of ultrasonic noise just to support the weight of a water droplet or a tiny plastic bead. Acoustic tweezers offer incredible precision for micro-objects, but holding up the sheer mass of a human requires a much heavier hitting force. Now, that brings us to the force of electromagnetism. As a fundamental physical force, it is staggering, roughly 10 to the power of 40 times stronger than gravity, but utilizing it is notoriously difficult. Standard magnets are inherently unstable. If you try to balance two opposing magnetic poles, they constantly try to flip over and attract one another. To get around this instability, engineers rely on a process called magnetic induction. If you take a heavy magnet and drop it through a hollow copper pipe, it falls in slow motion. This cross-section demonstrates why. As the magnet falls, its magnetic field moves through the conductive copper, inducing a secondary opposing magnetic field pointing upward. This creates an invisible cushion that physically resists the drop. Modern hover engines use internal motors to rapidly spin magnets over conductive metallic surfaces, constantly regenerating that upward push to hold extremely heavy weights. But because this system relies on spinning motors, it violates our strict rule against moving parts. To truly float a human payload, we need a material that locks perfectly still. The answer lies in a highly specialized class of materials known as ceramic superconductors. These ceramics exhibit bizarre physics, but only under extreme conditions. To activate their unique properties, these ceramics must be frozen with liquid nitrogen to around -200 degrees Celsius. At this freezing threshold, the ceramic entirely loses its electrical resistance. Energy flows through the material without leaking, scattering, or slowing down. Notice what happens in this diagram when the frozen superconductor is placed over a magnetic track. The magnetic field lines actually pierce through the disk. This anchors the material in midair, completely neutralizing its urge to flip or slide away. Because this lock is entirely rigid, it scales up beautifully. Pack enough of these super-cooled pucks onto a board, and they easily hold the 100-kilogram weight of a human rider. By combining extreme cold with electromagnetism, scientists have solved the stability problem, allowing massive objects to float in midair without any mechanical aid. These physics breakthroughs are rapidly moving out of controlled laboratories and scaling into massive real-world applications. Take sonic levitation. Very soon, doctors will use focused acoustic tweezers to push capsules of medicine directly to specific organs or break apart tumors without making a single surgical incision. On a larger scale, engineers are scaling up superconductor technology to propel friction-free mass transit pods at the speed of commercial airplanes. There are even architectural plans to embed heavy-duty hover engines directly beneath foundations. During a catastrophic earthquake, these systems could briefly detach entire buildings from the violently shaking earth to prevent them from collapsing. Mastering levitation provides a practical tool to bypass gravity itself. By holding matter perfectly still in midair, we gain entirely new ways to build our cities, treat our bodies, and move across the planet.